Today we're looking at isotopes, a word that I've actually said more than once in here, but today you're going to get a mastery of what isotopes are and how we can calculate what's called average atomic mass using isotopes. So let's start off by looking at rubidium. Find rubidium on your periodic table. And write this down. This is a couple hyphen notations of rubidium. In these two hyphen notations, what are the numbers? That 85, that tells me what about that rubidium? The mass. The mass. The only number that hyphen notation gives you is the mass. All right? So this rubidium has a mass of 87. These are two isotopes of rubidium. Again, isotopes being the same element, but multiple versions of the element existing in different masses. Now, if I compare these two isotopes together, there's a couple things they have in common, and that's the biggest thing to grasp here, is because I can ask you a bunch of comparison questions and try to trip you up, and you'll miss them if you're fuzzy on what these two isotopes refer to. If I were to get a proton, electron, and neutron count on each of them, all right, they would have some things that are the same and then have one thing that's different. What do we know must be the same if they're both rubidium? The protons. Protons give identity. If you change the protons, you change the element. So if they're both rubidium, they both must have 37 protons. All right, 37 being the atomic number that we get from the periodic table. What else do they have in common? The electrons, because we know that right now, the protons and the electrons are always the same value. It's those neutrons that are different between the isotopes. It's the neutrons that make isotopes even exist. Because by changing the number of neutrons, I can alter the mass. Neutrons have mass. But it keeps the element the same. Only changing the protons would change the element. And of course we know that to find neutrons, that requires subtraction, right? We would take the mass, so for my rubidium 85, we would take his mass of 85, subtract 37, what do you get? 48. All right, so we've got 48 neutrons in rubidium 85, but then when I found the neutrons for rubidium 87, we would use that mass number of 87 minus 37, because it's still minus the atomic number, which never changes. And here you get 50. So look at those counts. Guys, this is the difference between all isotopes, is the neutron number. Look at your cheat sheet. It's got the definition right here. Isotope, an element that exists in different forms regarding mass, caused by a varying number of neutrons. I can't stress enough the different ways I can ask you about just the stuff that's on this board right now. So these are isotopes, and we'll be dealing with them using some math in a moment. But first, I want to explain why there's decimal numbers on your periodic table. Look at rubidium on your periodic table. You'll notice that it's not rubidium 85 and it's not rubidium 87. Instead, it's rubidium 85.468. Here's why. Look here. There's no such thing as rubidium 85.468. You can't have partial particles. You can't have 3.3 neutrons. They come in whole numbers. which means when you add the whole numbers together, the mass is a whole number. The reason that there's decimal numbers on your periodic table is that it's an average. These really are the two rubidiums that exist. There's rubidium 85 on planet Earth, and there's rubidium 87 on planet Earth. But one of them is far more common. Which one do you think is more common, 85 or 87? 85. The reason that 85 is more common is because if you look at the periodic table, what does it round to on there? It rounds to 85. The reason that it's a little bit bigger than 85, though, when you average it, is that rubidium 87 is out there, the one that has 50 neutrons instead of 48, but it's rare. We get that decimal number by using a percentage. What we're going to do in a moment is figure out how to calculate average atomic mass. But I could say something like, well, like 90%, or a problem here actually says it, 72% of all rubidiums are rubidium 85, all right? And 27% of all rubidiums are rubidium 87. And when you take that into account and average it in the way I'm about to show you to do, the fact that so many of them are rubidium 85 makes the average on the periodic table come closer to 85. In other words, open your brains right now. I want you to hear this sentence. The most common isotope of the elements can be found by looking at the periodic table. Yeah, it's a decimal number. It doesn't give you the exact number because it shows you that there are isotopes, and by averaging it, you're going to get a decimal. But if you round it, you'll get the most common isotope. What's the most common isotope of carbon? That's how it would be written. 12 is the answer. Sorry, I messed up my recording. It would say C12. What's the most common isotope of radon? Look bottom right. 222. Radon 222. For radon, that's the only isotope of radon. It doesn't have other isotopes, so it's just a whole number because it only comes as radon 222. What's the most common isotope of titanium? Titanium is element number 22. What's the most common isotope? Not 47. Round it. 48 is the most common. Do you think there is a titanium 47 though? There probably is. It's rare. And that's why the average is right below 48. But 48 is going to be the most common. But there are some other isotopes out there. Some other more rare versions. Any questions so far? In order to calculate average atomic mass, which will come out as a decimal number, just like they do on the periodic table, you're going to be given data like this. I'm going to pull the data out here on the whiteboard for my video people. But here's what question 1 says. You don't have to write the question. Just pull off the data with me. It says rubidium has 2 common isotopes. We just got done talking about rubidium. Rubidium 85 and rubidium 87. Now, notice how they list it in this problem. They go rubidium 85 and rubidium 87. Hey, what's the name of that notation? Hey, you got a cheat sheet out in front of you because I told you to have a cheat sheet out in front of you. Man, I bet you can find it fast. What is it? Hyphen notation is what we did a moment ago. You're disappointing me. Nuclear notation, because you're smart. Yeah, nuclear notation is the one where they use that exponent up there. All right. The one that I showed you for nuclear also have the atomic number down here on the bottom for the exponents. But you'll notice that since these problems are just focusing on the mass, and the mass is the top number, it's showing you different formats, just like I've already taught you different formats. So we've got rubidium 85 and rubidium 87, just like we did a moment ago. But not only does it give you that, it gives you their percentages, how often they occur in nature. Reading off the board, it says rubidium 85 occurs at an abundance of 72.2%. And it says rubidium 87, you're writing everything I write, that rubidium 87 exists at 27.8%. So right away, I can see that it's telling me rubidium 85 is more common, and this one's more rare. All right? But we can use these numbers in an equation to get an average atomic mass. Look at your cheat sheet at the bottom. You can see the equation. It's in bold. It says, and just reading off your cheat sheet, it says we need to take the isotope mass 1, multiply it times its percentage, and then add that to the next isotope mass times its percentage. So there's the equation. I'll show you how to plug it in. First off, percentages are no good in regards to doing this multiplication. They need to be decimal numbers, which once upon a time you learned how to turn a percentage into a decimal. But in case you forgot, 72.2% when written as a decimal is going to be, slide to the left twice, 0.722. In order to turn a percentage into a decimal, the decimal must be slid to the left twice. So 27.8% written as a decimal. Again, watch it. There's one slide right there. Another slide right there. Creates 0.278. It's these decimal numbers that need to go into our equation. So let's take a look at the equation then. Reading off your cheat sheet, it says isotope mass 1, my first isotope mass is 85, times the percent abundance written as a decimal. For the 85, the percent abundance as a decimal was 0.722. Plus my isotope mass number 2. Isotope mass 2 is 87. Times its percentage, 0.278. And by typing it into the calculator exactly like that, you'll get your answer. You'll get the average atomic mass, the decimal number of rubidium. So on my calculator, then, I'll type it in exactly the way I see it here. Open parentheses, the button above the 8. 85 times 0.722, close parentheses. The parentheses help with your order of operations. It's a good habit to be in for later math anyway. Plus, open parentheses, 87 times 0.278. What do you get? Yeah, I get about 85.56. Anybody remember what the units are? AMU, average, atomic mass units. And that's the answer to the problem. Let's do another one. I want to point out that the equation has an ellipses at the end. The ellipses is the dot, dot, dot. That means that this process right here could go on if there's more isotopes. There's some elements that have lots of isotopes, in which case you would just keep repeating the cookie cutter part of the equation in order to get the answer. I'll show you what I mean on this next one, because there will be more than 2 isotopes. There's a new problem posted on the board regarding uranium. It says uranium has 3 common isotopes. We've got uranium-234, 235, and 238, and it gives the percentages of each. So let's pull that information out here onto the whiteboard. So we've got uranium-234. We've got uranium-235 and uranium-238. I'm also going to pull out their percentages. It says the 234 exists at 0.01%. The 235 is at 0.71%. And the 238 is at 99.28%. Hey, which of these three numbers will our final answer be the closest to? The last one, right? Almost all of the uranium has a mass of 238. Almost all of it. But these other very rare isotopes exist, so we have to take them into account. What's the next step? Turn them into decimals. Guys, do not plug these percentage numbers into the equation. You'll be very mad at your answer, especially if I make that awful answer a choice. We need to slide the decimal to the left twice. Hey, watch this close. Watch this close. This one can get tricky. All right? Look where it is right now. It's already a 0.01. When I slide it to the left once, now it's 0.001. What happens when I slide it the second time? It creates a 0 in that placeholder. If you are weak on this kind of math, you need to come see me in tutoring so we can practice. This is going to be 0.0001. And that'll be the decimal number that gets plugged into the equation. So we slide this guy to the left twice. 1, 2. Again, it's going to create a 0 in the empty spot we've created. So I get 0.0071. And then here, slide to the left twice, and I get 0.9928. Is everybody with me? Now we're ready to plug into our equation. All right, and we know that the relevant information are these masses and these decimal numbers. So make sure that you've got that down. So here we go, following the equation. Isotope mass number 1 is 234. Multiply that by his percentage, 0.0001. Plus, remember, it's pluses that are going in between each set of data. The next mass is 235 times his mass of 0.0071. But now we've got another set of data, so plus, and it just rinses and repeats, 238 times 0.9928. Well, let's get to an answer. Open parentheses 234 times 0.0001, type it carefully, plus open parentheses 235 times 0.0071, close parentheses, plus open 238 times 0.9928, close. I get 237.98 AMUs. What do you think? And just to review, because yes, being able to do the math is important, but understanding the concept is too. These are 3 different isotopes of uranium. The only difference between uranium-234, 235, and 238 is the number of neutrons. That's the only difference, is the neutrons exist in different numbers.